Catholic University of Leuven, and now he is a postdoctoral research fellow from the same university. Then we're very glad to having you here, Rocco. We'll start with your talk.
Okay, hello everybody, and thanks Diego for the nice introduction. So we will talk about clustering time-varying data, as you can see from the title. This is a brief outline of the presentation. So we will start with a general introduction.
Rocco,
then yes.
sorry for the interruption. If you don't mind, we would like to see you. If you can turn on your webcam.
Yes, sure. Yes, sure. I thought that because of the connection problem, it was better to keep the video off. But yeah, it's as far as it is fine with you, it's also fine with me.
Yeah. But I think many people here will be happy to see you, especially women. Okay, thanks.
Okay, so this is the outline of the presentation. So we will give a general introduction, then we will say what is machine learning, then we will talk about static and dynamic clustering, and in the end we will give some conclusions. And this presentation is mainly based on the PhD, on my PhD work. So as introduction, let's see, there is some problem with the presentation. Okay, so you all know that we are in the era of big data. We have data coming from different sources, like our activity on social networks or sensor networks, bioinformatics, and so on. So of course there are different ways to analyze this data. In my case, I was focused on clustering. So also many data sets can be represented as networks. For instance, in this picture you see a configuration of the internet in 2007. And in case of networks, if you want to find groups of similar nodes, clustering is called community detection. So we will talk about community detection in static and evolving networks. Also, we talk about clustering of stationary and non-stationary data. And also, we will emphasize the fact that the models that we develop allows to select, for instance, the optimal number of clusters that are present in the data, and also allows to predict, given a new data, to predict the cluster membership based on the model that was learned during the training phase. And also, yeah, as we said, since we are in the era of big data, we would like the algorithms to be scalable, so such that we can use to analyze large data sets. So then now let's give a general overview about machine learning. So what is machine learning? Machine learning allows to develop algorithms which can learn from data. And during the learning process, there are different phases. First of all, we have to represent your learning process by means, for instance, an optimization function. Then you need some solvers to find, for instance, an optimum of this objective that represent your learning problem. And then you need some ways of evaluate the performance of the method. And it's very important that you don't build a model that just memorize the data that you have, but the model should also be able to generalize from examples. So Mao should have learned the basic relationship that are hidden in the data, the important patterns, um, and then should be able to then to not simply memorize the data. So machine learning is used in many applications, like when you look for some content in Google, there is a machine learning algorithm that is ranking the web pages based on the patterns of ingoing and outgoing connections between the web pages. Or in your email client, there is an automatic software that sometimes doesn't work very well to distinguish between normal emails or spam. Also, in recommender systems, there are machine learning algorithms that advise you about watching a movie or buying a new book based on your past preferences or your similarity with other users. And also, for instance, in fraud detection, people use machine learning algorithms to detect, for instance, when your credit card got stolen, and then it should be blocked, let's say. Machine learning, of course, in machine learning there are a lot of algorithms. Artificial neural network are among the most successful methods. They mimic the way the information is processed in our brain. Basically, every neuron does a very simple job. Just take some inputs, apply some transformation, sum the inputs, apply some transformation, then give an output. But if you put several neurons together that do every neuron does this simple task, then complex behavior that we call intelligence emerge from this network of neurons. And a major drawback of artificial neural network is that when you want to optimize the error as the function of the weights between these neurons, you can encounter many local optima in the cost function. If you don't have good algorithms to, let's say, avoid these local optima, it can give you not so satisfactory results. Recently, support vector machine have become more and more famous as an alternative to artificial neural networks as a learning algorithm. Support vector machine are so-called kernel-based methods. It means that you have your input data, you transform this data using a so-called feature map. So you bring this data in a new space where it's easier to, for instance, to classify the data, as you can see in the picture on the left. Also, you have two different representations for the same problem that are called the primal and dual framework. And then, based on the kind of data that you have, you can decide to solve the problem in the primal space or in the dual space. In this work, we have used a particular class of SVM that is called the least square SVM. Where you have equality instead of inequality constraints and a quadratic loss function, but don't worry about the details. So we say that we are interested in clustering. which is an unsupervised pattern recognition method. As humans, we are very good in performing pattern recognition, like for instance, when we see a friend in the street, we recognize it. Also, so clustering is a way to perform pattern recognition where you don't have any label available, and you want to organize your data into meaningful groups. For instance, in the picture that you see on the in the bottom, this picture is related to a research did by some, I think, some Brazilian researchers, where they analyze a data set from a website where people go there and say, for instance, what they are drinking or eating, and they give a rating. So they took this data, they applied clustering, and they found something very interesting. In particular, for instance, they saw that the drinking habits of Brazilian and French people are very similar, though these countries are quite far. So they discovered by means of clustering that not always the cultural boundaries correspond to geographical boundaries. So this was nice example of clustering applied to a real data set. So now let's talk about static clustering. In particular, we will use this model that is called the kernel spectral clustering. Okay, don't worry again about the math if you don't understand it. You just should be aware that this clustering method is embedded in a learning framework. So you can train your model on a subset of the data, and then you can also, once you obtain your model, you can, as I said before, you can, given a new point, you can predict to which cluster it belongs without performing train again. And this is so a quite powerful property of this method that not many methods have. And also you can perform model selection to select the optimal number of clusters. So this is like this is let's say the modeling pictures. So you see you have an input data, for instance a network, and then you compute the so-called kernel matrix, which is actually the omega in equation, in the dual equation. Then you basically you solve the eigenvalue problem. So you find the eigenvectors, you take the sign of these eigenvectors, and this gives you some cluster prototype. Then whenever you have a new point, what you do, you compute this function, the equation 3, you take the sign, and then you compare the this binary string related to this new point with all the code book, and you assign then the point to the closest prototype in the code book. By using, for instance, the Hamming distance between binary strings. Also, so this is an hard clustering. It's called hard clustering method. In many applications, you are interested in find soft clustering. In the sense that in many applications, for instance, like suppose you want to analyze you want to do sentiment analysis in Twitter. So you can each, for instance, a tweet can be sad, can be angry, can be happy, but there is a degree of happiness or angriness, let's say, that you can find only using, for instance, soft clustering. Or in social networks, a person can belong to several communities at the same time. So in all these cases, you can use soft clustering rather than hard clustering, which give you more interpretable results. So then, okay, we have, I don't go into details, but we have proposed an extension of the model that you saw before to perform soft clustering. And this is what you obtain. So here you see that there are three clusters, three Gaussian clouds, and then here you see the output of the model. So you see that the model for the points that are on the bottom predicts assign this point to one cluster, and then the membership of the points decrease when you go far away from the center that is indicated with the square, the black square. And also you see that on the table in the bottom that if you compare the KSC with soft KSC, the soft clustering method has a better performance because the clusters are very overlapping. So in this case, soft clustering is known to perform better than hard clustering. You can interrupt me when you want, if in case you feel that I may go too fast. So let me know if I'm going too fast, or is that fine, Diego?
Yes, it's fine.
Okay. Um, so now let's talk about networks. So networks describe the interaction between objects in complex systems, like in biological pathways. You have networks of networks of interaction between proteins, for instance, or in telecommunications, all the satellites communicate with each other, and this can be described as a network, and so on, like in food web, trade networks. So many complex systems can be described as networks. And one possible analysis that you can perform on network is the community detection, that, as we said in the beginning, is just another name for clustering the nodes of the network. And this community detection is very useful for different reasons, like suppose some proteins bind together very closely, then this community of proteins can be associated to some important function in the network of proteins. Or like in each community, if you have a social network and you split in different communities, maybe in each community there are more influential nodes, or there are nodes that act as bridges between different communities, and this can be very useful to know if, for instance, you are studying the spread of epidemic diseases, for instance. And also, if you have a network, suppose with millions of nodes, it's very difficult to visualize. So if you visualize in terms of communities, it is much more, it is much better. You don't have many problems of visualization if the communities are not so in large number. Here we have applied the KSC, the model that you saw before, for community detection. And since it is a kernel method, you have to choose a kernel function to describe the similarity between the nodes, and also to train your model, you have to extract a subgraph from the whole network, and also you would like to select the optimal number of clusters and to not let the method be too slow. So regarding the kernel function, we have used two main type of kernels. The community kernel says that two nodes are similar if their common neighbors share many connections, as you can see on the left. The cosine kernel basically just consider each node as a vector and then takes the angle between the nodes to describe the similarity between these vectors. Also, okay, we have proposed a method to extract a representative subgraph from the whole network, which is representative of all the communities that are there. Why we need this? Because suppose you just take random nodes, it can be that you take nodes also only from some communities and not from the others. So in this case, with this method, we have shown that we can take nodes from all the communities that are in the entire network. The problem with this method is that it is not so fast. So then we have proposed other methods for the same purpose. So regarding the selection of the number of clusters, we have used modularity. So basically, modularity tells you how strong is the community structure. Since you don't know how many clusters are there, what you do, you define a grid with the different number of clusters, and then for every you partition your network, and then basically for each number of cluster you compute the modularity value, and then you take the number of clusters corresponding to the maximum of the modularity. Like for instance, you see here two examples. In the picture on the left, the optimal number of cluster is 7. In the picture on the right is around 16. And these are two real networks. The one on the left is the network of interaction between proteins in the yeast, and the one on the right is a network of generators, electrical generators in USA. So yeah, the problem with this method is that if you are not able to select a small training set, then in the worst case scenario, the complexity is quadratic. But in case you are able to extract a good and small training set, then the complexity is linear with respect to the total number of nodes that we denote with n. We have, let's say, improved the basic method to handle big data by, as I said before, by using a fast technique to select the training set. Then we have also proposed a self-tuning method that doesn't need to compute, for instance, the modularity as we did before to select an optimal number of clusters. And also, if you have a big test set, you can divide into different parts, and you can perform the prediction of the membership for all the test set in parallel, because you divide in different parts and then you split in parallel. So then, if we have compared the KSC with the other methods that you see in the table, like the Louvain method, the Infomat, which are very famous methods, and we have observed that our method performs better than others in terms of conductance. It's a measure, another measure. And the Louvain method is the best in terms of modularity, that we have indicated with the Q. So this was a quite interesting result. So now let's talk about dynamic clustering. So in many applications, the data change over time. Like if you want to find communities in a network that is evolving. Suppose you want to find communities in your Facebook network today, then in 1 month, then in 2 months, and so on. Or in application like object tracking in video surveillance or in traffic jam predictions. These are data that evolve over time. By the way, I stole this picture from a presentation of Diego, so I hope Diego will not be sorry for that. Um, so, so then if you want to apply clustering, in this case, you have to incorporate some kind of dynamics in the clustering model. Suppose you have an evolving network, which can be described as a sequence of networks over time. If you apply a static method at each time, this is not so advisable, because by doing that, your clustering results are high sensitive to noise and are not able to explain the long-term dynamics of the communities. So what we did, we have proposed an extension of the model that you saw before, that we call kernel spectral clustering with memory. And this is the model. So you see that the first two terms in the objective function are the same as before. And then you have another term which try to maximize the correlation between the actual model and the previous models, because you want to keep track of the evolution. You don't want that the model that you have at time t is completely different from the models that you had at the previous times. With the nu, we have indicated the smoothness parameter, and m indicates the memory, mean how many snapshots in the past you want to consider. Regarding nu, we have two frameworks. In first framework, you can simply fix nu to 1, so saying that you want to smooth always the results. Or in the second framework, you select an optimal nu. So basically, nu, the smoothness get activated only when there is a big change in the network. And here you see an example on the reality mining dataset, which is a dataset consisting of networks of students at MIT, network of proximity. So these students participated into an experiment with they were wearing some Bluetooth devices, and the Bluetooth devices were registering when the students were close to each other. So then you could, the researcher have constructed the networks with these students where two students were connected if they were enough close. And you have a network every week. So you can see here that the the smoothness parameter get activated around some dates, like fall term start, winter term start, and winter term end, which are dates when there are big rearrangements in the network, because, for instance, students went on holidays, or they came back from holidays, so some students maybe are sick, and so on. So then in this case, the method is able to recognize when there is change and then to activate the smoothness which is then necessary to keep track of the evolution of the network. Then, since at each time the membership that the algorithm produces are arbitrary, because clustering is an unsupervised method, so you don't have labels. The labels that you produce can change every time, and this does not affect the quality of the clustering results. Then you need a way to keep track of the evolution. So what we did, we construct a network between the communities at different successive timestamps, to then to keep track to understand, for instance, what the community CI became from time t minus 1 to time t. And also we have proposed a visualization of the dynamics in terms of a 3D space, where basically you have each community is represented as a sphere, as you see on the top, and the size of the sphere is proportional to the number of nodes belonging to that community. So then you can easily see, for instance, that the community C4, which is the purple one, split in two, or the green community became smaller, and so on. And also you have another visualization in terms of the network that we construct for tracking that you see on the bottom. But I think the top visualization is more clear. So then we have applied clustering for performing fault detection in industrial machine. So in industries, we have these machines that are running continuously, but sometimes it can happen that they stop working. So you would like to avoid, or at least to minimize the time that the machine are under maintenance. Also because this is safer, it's safer and reduce the costs, because when the machine is stopped, you are not producing anything. So we have a data set which comes from a packing machine, as the picture that you see on the left. So you have this machine that is sealing bags, is closing bags, and some accelerometers are registering some signals at every time the machine seal a bag. Yeah, the kind of vibration signal that you have are showed on the right. So here, to perform dynamic clustering, we have used KSC. We have used the static model, but we have incorporated the dynamics in the pre-processing step. So instead of considering one signal at time, we have put concatenated different signals together, and a window signal now is a data point. So in this way, also if you apply a static algorithm, you can catch the degradation process going on. So here I can show you a video if we manage. Let's see. It's a bit slow, but okay. Yeah, so you see on top you have these signals that are coming from the machine, and in the bottom you have the output of the clustering model. The black lines that you see, the vertical black lines, are the moments when the the operator stopped the machine to clean the sealing jaws to perform the maintenance. So you can see that much before the actual maintenance, the method could automatically detect that the machine was not working properly. It jumped from the green cluster, which is the normal cluster, to the red cluster, which we call the maintenance cluster. Um, and then this information can be very useful, for instance, to try to perform maintenance at the right time, to not lose, let's say, money, and to be safer. So now we can close the video and go back to the presentation. Okay, then in this case, what in the case of the machine, what we have done was that we have trained the model to recognize only these two regimes. The let's say the good clustering, the good regime, and the faulty regime, and we assume that we assume that the machine will not know other kind of regime, so you have only these two configurations. But in some cases, your initial distribution change over time, so you can have different regimes that appear over time. So the model that you train in the beginning will not be a good like in future, because the data changed. So we call this process, we call this kind of data non-stationary data. So we have proposed a way to basically to update the initial model, that we call this algorithm incremental kernel spectral clustering. And basically, whenever a new point arrives, you always update the model such that you can handle this non-stationary behavior. Okay, this is a scheme that summarize the working mechanism of the method. Yeah, don't worry about the details. The important thing to know is that you don't have a fixed method that you apply every time, but this algorithm gets updated. To see if the method was working, we have applied to a data set of PM10 concentration monitoring station. So every station is measuring some pollution. So we have this time series of pollution, as you can see, or pollutant concentrations, as you can see on the bottom. And what we have done here was to train an initial model in the first 72 hours, so in the beginning, and then we applied a sliding window approach to see if the initial model was able to get updated. And so here I can show you another video. Let's see. Okay. So you see, in the beginning, the method detected two clusters, but then at a certain point, you see that a new cluster appears. Why this cluster appears? Well, if you remember the time series, at one point there is a huge peak, and this peak was due to some strong winds that were bringing pollutants from Eastern Europe to this part of Europe that comprise Belgium, Netherlands, Germany, and Luxembourg. So then when the window entered the region when there is this peak, the method detected that there was a big change and then created the blue cluster. And as you saw, when the window went far away from this region, then the blue cluster gets disappeared. So then we could see that the incremental algorithm was able to recognize this non-stationary behavior of the pollution concentration over time. So here we can conclude our talk. So I showed you in the beginning a soft clustering approach. Then I showed you how we can perform community detection in networks. Then I introduced the KSC with memory to cluster dynamic time evolving networks. Then we have saw an application of KSC for predictive maintenance, and finally we have seen the incremental KSC algorithm. So here there are some publications where you can read more about these results. And then I want to thank all my co-authors, and maybe for you it would be nice to see that in between these co-authors there are three Colombians like Carlos, Oscar, Mauricio, and Diego, Professor Diego. So it's let's say a good hope that also you maybe in the future you can become if you are interested successful researchers. Thank you for your attention, and if you have some questions you can ask me.
Thank you, Rocco. Let's thank the
Yeah.
speaker, please.
Thank you, thank you, thank you very much.
Okay, we have time for some questions. People here in the conference room, any question for Rocco? We have one question, Rocco.
Yes.
Hi, hello.
Hello.
Excuse me.
Yes.
How these predictive algorithms, like the last one you explained,
Yes.
can be applied to economics, like the stock market? Or can it, or they maybe the variables are too unpredictable? I don't know. Can they?
Um, well, in principle, yeah, as you said, the economic time series have high volatility. So it's if you want to predict exactly what will be like the future value of a stock index, this is not this is quite a difficult problem. But in this case, we want to have a less precise prediction, in the sense that we are not interested uh, in the actual value of the stock index, but only if there are some big changes with respect to previous situations. So I guess that you can apply the method also if also in this case. But yeah, you will not predict exactly what is the value of the stock index, but maybe you can predict some change with respect to the previous situation.
Okay. Any other question here? People attending online, any question or any comment? Maybe you want to say hello or say thank you to Rocco? Somebody? No, so good. Okay, thank you. Thank you, it was very interesting. Anyone else? Okay, I have some questions. First of all, thank you very much for accepting our invitation, Rocco. It's
Yeah.
uh, it's uh, it's an honor to us to having you here at least online, at least in this video conference. Hopefully, in the future, we'll bring you here in person to give us a conference, or even better, a whole course on clustering. Okay,
Yeah,
Rocco. Well, uh, we have to talk about the copyrights about the using my picture. And,
yeah,
here here we have some copyright procedures, very strict. Then you have to be careful about it. Just kidding. Okay. Well. Uh. Uh. Well, I have some technical questions.
yes.
Uh, to me, it was interesting to see how you visualize them in the. I think it was in the slide 32. I
The
think 32. I think.
um, this one.
Yes. Could you exactly? Could you explain it again? Because now we're working on data visualization. Then it would be
Yes.
interesting to listen again your explanation. Thank you.
Yes. So basically, you see. Okay, you see here in the dual problem, you find your solution is expressed by these um, alpha TL vectors. So then what we do, we take the we take a 3D embedding given by alpha 1, alpha 2, and alpha 3, and then um, we draw some. So we find the centers of the clusters in this alpha space, and then we draw a sphere around each center with dimension proportional to the number of points belonging to that cluster. So it's based on the dual solution vector.
I see. Thank you.
Yeah.
And the size of the circle. What's the meaning of the
Yes.
size? Is
Yeah,
the
so basically, suppose in cluster one, in the green one, you have, I don't know, let's say 50 points you draw with a certain size. And if in cluster four you have, let's say, 70 points, you have to draw it larger because it has more points than cluster one.
okay? Thank
So
you.
the size is given by the number of points belonging to that cluster.
I see. Thank you. Um, well, another question is when you showed us uh, the maintenance application,
Yes.
we could see that okay, you could detect in advance. How long in advance was detected?
Uh, mm, let's see. This is so you had basically one data point every 2 seconds. So here there are, I don't know, let's say from uh, maybe it is 200 seconds or something like that. Because yeah, you have a data point every 2 seconds in this case. So you see that you start to detect here, which is around, I don't know, maybe 180, and then um, this is, yeah, maybe 250 or so, yeah, maybe a couple of minutes, I don't know, something like that.
Yeah, yeah. Well, my question is, it's because it's that enough. The that time it's good enough to detect in advance the fault.
Yes.
Okay, because
No, sorry, maybe maybe can you repeat the question because
yeah,
there
yeah,
was
of
a
course. It's the time that
yes.
you detect in advance the fault that
Yes.
you can predict the fault. Is that enough? I mean, it's good enough time.
If it's enough, yeah. In this case, actually, our method was not because since it was in a big project with other partners, our method has not been directly used to optimize the maintenance, the time of maintenance, but we gave the output of our method. So we gave this um, yeah, not exactly this output, but the latent variable behind this binary clustering. We gave our output to another method which used our output as a kind of additional features to add to the signals, and then that method was optimized the time of maintenance also based on some real costs to produce each bag. So apparently it was enough because they showed, the other partners showed that by using our output they were able to save some money by performing the maintenance at not at these times where there are the black lines, but maybe a little bit before. So yeah, in this case it was okay, but yeah, maybe in other applications 2 minutes is too close to the failing, let's say, to the failing of the machine. So depends, I think, on the given machine, on the application.
Then your clustering outcomes from this method are applied to fit maybe another methods, another algorithms, or
Yes,
concentric block from another application. Okay, I see. Thank you. Okay,
yes,
two couple of questions more. Um, I'd like to I'd like you to tell us what was
yes.
your intuition, what was your first or your initial idea to start with dynamic clustering, and why you decided to create a dynamic model using KSE, and especially that one called you call it um, well, no, not the incremental one, the other one is called
With memory, yes.
exactly the memory effect clustering.
Yeah, okay. So I did I didn't decide to work on dynamic clustering, but when I joined the group of Professor Soikens that you also know, um, he proposed me to work on dynamic clustering. So then I accepted the challenge in the beginning of PhD, and so then it's the let's say the reason. Um, why I started from KSC to create the KSC with memory. It's because when I started the PhD, there was there was a postdoc, a Colombian postdoc, Carlos, Carlos Alzate. I don't remember if you knew him. Yeah, I think you knew him. You also had some a paper together. And so, since Carlos was helping me in the beginning of PhD, and he created the KSC algorithm, then for me it was easier to start from the KSC algorithm and try to understand how it could be extended to dynamic scenarios, because I had, let's say, I had Carlos that was supervising me, and so it was easier.
Thank you. Yeah, that happens to me. It was the same when I when I decided to stop for a while, and I was wondering, hey, why I'm working on this, why I'm doing this PhD and this topic, and that happens. Yes. Um, Actually, we worked in a similar framework.
Yeah.
Well, and the last question, Rocco, in order to finish, um, we would like to listen from you. Um, what's next? What are the challenges? How can you encourage, especially young researchers, to start with clustering and dynamic data analysis in general?
Well, today many say fancy companies like Facebook, Google, IBM, um, they are more and more interested in machine learning methods that are able to process dynamic data. So if you would like to work for instance, one of these uh, big and important companies, you you are welcome to study to research on the let's say methods able to perform dynamic data analysis. But in general, since basically all the data that we have are naturally evolving over time, in whatever application you think about, it you can give a richer description of your data, or you can perform better predictions um, if you develop some methods that incorporate the dynamics, let's say.
Okay. Thank you. Grazie mille, Rocco.
Prego.
And what about your
Your Italian
Spanish?
is very good.
Something in Spanish, maybe bye.
Um, Adiós, ¿no?
Yes.
Adiós, buenas tardes a todos.
Thank you.
Eh,
Gracias.
muchas gracias por la invitación y por escuchar la presentación. No sé si está correcto o no.
Es correcto. Muy bien. Thank you very much. Let's thank the speaker again.
Okay, thank you very much, and yeah, have a nice continuation there in Colombia. Here is already it's already night, so it's not time anymore to study. But there, I suppose it's still day, so you will have a long day.
Okay. Thank you. Have a good night.
Okay, see you. Have a nice day. Bye.